Good morning, my dear students. In this video, I will discuss about portal frames. This is in Mumbai University semester 9, Theory of Structure 8 for architecture students. Let us start. What is portal frame? A portal frame is designed to carry load. But from structural analysis view, it can be classified in two categories. Number 1, non-sway. Number 2, sway. What do we understand by non-sway portal frame? Non-sway means in these non-sway portal frames, two columns of the portal frames, they are identical. Identical in the sense they are identical in end conditions. End conditions means either both the supports should be fixed support or both the support should be hinge support, like that. So they are identical end conditions. Number 2, the loading should be symmetrical, and in this way the frame will not sway. So here you can see two examples. In the first example I have shown you that you can see the supports are the fixed support. Two loads are acting, horizontal loads are acting at the left column and the right column. Their value is P and they are acting at the same height from the base, L1, L1. And there is also one UDL acting, W per meter run or W per unit run, that is also placed on the horizontal span of the or horizontal part of the portal frame. So the first is the example of the non-sway, because here the end conditions are identical, both are fixed support, loading is symmetrical. So this is a non-sway frame. Portal frame. The right hand side, another example I have shown just to give you an idea that identical end condition doesn't mean that it may be always it should be fixed support. It may be hinge support also. So the next example, right hand side example you can see over here, they are the hinge support portal frame, and you see that from the base at L1 height UDL is acting on both the sides, so it is identical, and also one point load is acting, and it is also acting at the midpoint of the horizontal span, so loading is also symmetrical. So these both are the example of the non-sway portal frame. Now let us have a look at the sway portal frame. So obviously that is just the opposite of the non-sway portal frame. Sway portal frames, columns are not identical and the end conditions are also different. Number 1, there may be 3 different end conditions. Number 1, both ends are fixed. You can see the diagram, I have shown it at the left one. So both ends fixed. Then there will be the next case is the both ends hinge. And the last case is one end fix and one end hinge. So this is about the introduction about the portal frame. In this video I will discuss about the non-sway portal frame. As this course is meant for the architecture students, only the basic will be the basic of the portal frames will be discussed over here, which I think will be sufficient for you. Now let us see that before starting of the numerical, let us just note down the steps first. I would suggest you that you please note it down in your notebook. After that, when I will start the numerical, you try to solve it on your own and then look for the solution or proceed with the video. So let us have a look at the steps first. Step number 1. In step number 1, first we should find out the distribution factor. This concept, distribution factor, fixed end moment distribution method, you have already learned in semester 4. So here also I will take a quick recap that how to do all these things. So let us have a look at the first step. Step number 1 is the distribution factor. So to find out the distribution factor, first we have to find out the stiffness of the different member. So please pay attention over here that here I have drawn one portal frame ABCD. Now stiffness is denoted as K. So for AB and CD, the stiffness is 0. Okay, so as this end is the both the ends are hinged and AB and CD stiffness is 0. Now stiffness for BA and CD, so that will be 3 EI by L. Why this formula we are using? Because the further end means for BA, while we are talking about BA, what is the further end? Further end is A, because we are taking the, or we are pronouncing it as BA. So the further end is A. And when we are telling that CD, what is the further end? Further end is D. So in this case, the further end A and D, they are hinge or the simply supported. So for this case, the stiffness factor is 3 EI by L, where E is the modulus of elasticity, I is the moment of inertia, and L is the length of the member BA and CD. Okay, so now let us have a look of the stiffness of BC or CB. So in this case, BC or CB, the value of stiffness will be EI by L, because when we are considering or when we are talking about BC member, BC, these act as a fixed joint. So please remember or understand this concept of the stiffness value. Now next, how we can find out the distribution factor for BA. Now remember, distribution factor is always found out for a joint. Joint means, what are the joints over here? Joint is B, joint is C. So for a joint, we can find out the distribution factor. So BA, distribution factor BA will be stiffness of BA divided by the summation of the stiffness of the other the members which are contributing towards the joint. I repeat, this is the joint B. So how many members are there at the joint B? BA and BC. So in the denominator, it will be KBA plus KBC, and in the numerator, it will be KBA. We are finding out the distribution factor of BA. So distribution factor BA is KBA divided by KBA plus KBC. So we can find distribution factor of BA. Similarly, we can find the distribution factor for BC also. And also remember that summation of distribution factor for for any joint is always 1. We will see this point while we start with the numerical. Now the next step for the portal frame is we have to find the fixed end moment. Now for you currently, you just remember these two formula. There may be numerous variations of this portal frame problem which are done by the civil engineering graduate students, but for you architecture students, I think these two formula is sufficient. You understand this much, so you can always improvise or learn on it in future if you want to. So the fixed end moment, for this case, you please understand that the first case I have shown it is a point load W which is acting at the midspan L by 2, L by 2. So fixed end moment of AB will be minus WL by 8, and for BA it will be plus WL by 8. So this is according to our notation. And remember, C is the midpoint. So bending moment at C will be WL by 4, but it will be positive. Okay. Similarly, for the second case, fixed beam with a UDL throughout the span, W Newton per meter, the FEM AB will be minus WL square by 12, and FEM BA will be plus WL square by 12, and bending moment at C will be WL square by 8. And the step number 3 is you apply the moment distribution method, and then you draw the BMD, bending moment diagram, and also you find out the support reaction. Let us solve one numerical. This is one question given. So the question is, analyze the portal frame, draw the bending moment diagram, and find out the support reaction. So let us start. As I have discussed that the first step is to find out the distribution factor. To find out the distribution factor, first we are doing it as the stiffness of BA. So the stiffness of BA, the formula was 3 EI by 4L. So 3 EI by 4L. L is what? 4 meter. For the member BA, what is the length? Length is 4 meter. And you can see over here from here that KBA, stiffness of BA, and stiffness of CD is also same, because here we have taken the non-sway frame, the identical members, both the members are identical, load is symmetrical. So BA whatever will be the stiffness, CD will be the stiffness. So I have written it in one go. Next is KBC. Stiffness of BC will be what? EI by L, as I have told that it is assumed to be as the fixed joint. So EI by what is L of BC? Length of BC is 4 meter. So again BC stiffness is equal to the CB stiffness. Now next step is the distribution factor of BA. Distribution factor of BA is KBA divided by the summation of KBA plus KBC. So put the value KBA is 3EI by 16 and divided by 3EI by 16 plus EI by 4. So if you solve it, so EI cancels out and we get 3 by 7. So DF of BA is equal to 3 by 7 and this is the DF of CD also. Similarly, we can find out the value of DF BC, distribution factor BC. So it is KBC divided by KBA plus KBC. So this is also EI by 4 and divided by EI by 4 plus 3 EI by 16. So from here we can get 4 by 7 and this is also the distribution factor of CB. So from here we will go now to step number 2, that is the fixed end moment. As I have explained you earlier that MAB and MBA, fixed end moment at AB, BA, CD, DA, they are all 0 because there is they are the hinge support. So there is no fixed end moment. Now FEM BC will be minus WL by 8 as I have shown you earlier. So this comes out to be minus 6 kilonewton meter and FEM CB will be plus 6 kilonewton meter. And bending moment at E, that is the midpoint, it will be WL by 4 which gives us as plus 12. So here I will as I have told you earlier also, please note down the problem, go step by step, then only you will be able to understand and follow as I am proceeding. Let us start with the moment step 3, that is the moment distribution method. Please write down the table first. The first row is the joint. So what are the joints over here? A, B, C, D. 4 joints are there. Then in the next row you write member. What are the members? So if we start with joint A, the member is AB. Then at joint B it is BA and BC. Joint C it is CB and CD. And joint D it is DA. So next row you write it as distribution factor. As I have told you, the value you have got it as distribution factor 3 by 7, 4 by 7 and again you see 4 by 7 and 3 by 7. So I hope you have already written my previous step, so it will be easier for you to understand. The next step is the fixed end moment. Fixed end moment, as I have told you, at the AB and at the value of the DA, they are the hinge support. So there it is 0. Now let us start with the fixed end moment as we have found it as minus 6 and plus 6. For BC it is minus 6, for CB it is plus 6. Now the moment distribution method is very simple. In this case we have to balance and carry over, balance and carry over. We have to proceed it like this way. Let us start. After the FEM I have written the next step as the balance. Balance means here what you have to do, concentrate on the joint B. On joint B, what is the value of fixed end moment? Minus 6 I have written over here. We have found out minus 6, correct? Now this minus 6 value we have to distribute in both the members of the joint B. What are the members? BA and BC are the member. So this minus 6 value we have to distribute in BA and BC, but in what ratio? In the ratio of distribution factor. What are the distribution factor? 3 by 7, 4 by 7. So how does this value come? 2.57 and 3.43. Listen over here. 6 multiplied by 3 by 7 comes out to be 2.57. 6 multiplied by 4 by 7 comes out to be 3.43. Now remember one thing, we are using the word balance. Balance means what? Minus 6 is the fixed end moment. So if we have to balance that minus moment, we have to give both these values as positive, because minus 6 can be balanced only by positive 6 plus 6, and plus 6 how we will give? With the ratio of the 3/7 and 4/7. I am continuing with the same row, balance first row. Now here you see CB, what is the value of the FEM? Plus 6. Now plus 6 you have to distribute in CB and CD. So both will be minus, because plus 6 can be balanced only with a minus negative moment. But how we will balance it? Plus 6 multiplied by 4/7, that is 3.43. Plus 6 multiplied by 3/7, that is 2.57, and give it with minus because we are balancing it. Positive can be balanced only by negative. So this thing you have to keep it in mind, because sometimes we forget that this plus minus thing, but remember and write it like this way as I have shown. Let me explain the next step, carry over. Carry over means we carry over whatever now the moment is distributed, we carry over it as the half of the value. That means plus 3.43 we have done half value, that is 1.72 plus 1.72, and minus 3.43, that is we have carried over as minus 1.72, that is half of the value we carry over here. Okay, and after you have done it, again you do the balance. Balance means now what is the moment? Minus 1.72. So now how we will balance it? Minus 1.72 into 3/7, that is 0.74, minus 1.72 multiplied by 4/7, so it is 0.98, but it is minus 1.72. So how we can balance it? Both it should be plus. And just you see the right hand side part, that is already there as the 1.72. So when we are balancing it, both will be minus. So this process continue, and finally we are getting the moment value. Now here comes the question, till what point you should continue doing this? Till that point you should continue, till all the values come same. Because if you just stop any point, and okay, before completing one thing, please remember that we can end this moment distribution method only after the balance column, because the last step will be always balanced, because after just doing the carryover you cannot complete the table and take the sum. So what you have to do, the balance always should be the last step. Now you cannot stop anywhere in between, because all the value you can see at the last step, they are all same. So, and especially at the joint point, that is if you see, concentrate at the last line, that BA and BC both values are same, 3.6 and minus 3.6. Obviously they will be plus and minus, because by that way they are balancing the joint, or the joint is in equilibrium. That is a different story. They have to be plus and minus, but the values are same. So you have to reach that point. Now the question comes, ma'am, how we will understand that we are reaching the point? If you observe the table very carefully, if you see that as we proceed the step, the carry forward values, they are carry over values, they are becoming very less. Are you seeing? And the balance value also become less, because see, we have started with 6, and from here we have reached to 0.02. Correct? Now we have started, when we have started the value was FEM was 6, and now we have reached so 0.02. So here we can think of, maybe at that time we can take the summation and maybe the value will come same. So by that way, you can decide that okay, now the final stage has reached. Now let us look at the last step. This plus 3.6 minus 3.6, all these values, how you have got? You have done the summation from the first line of the balance. What was the first line? 2.57. See, from the value of the FEM. So from the value of the FEM you have to start and add all the values. So plus 3.6, how we have got it? Let us start with the value of AB, member AB. It was 0 initially, FEM 0, so finally it is 0, so it is direct. And then for the BA it was plus 2.57, plus 0.74, plus 0.21, plus 0.06, plus 0.02, like that way, 3.6. BC, how we have got? We have started with minus 6. Correct. Distribution factor you leave, because that is not the value of the moment. So we should start adding from the FEM value. So minus 6, plus 3.43, minus 1.72 till plus 0.02. So like that way we have reached to minus 3.6. And similarly for the member CB and CD. I hope that already you have noted down the problem. So now let us have a look that how we can draw the BMD, the last step number 4. So as I have told you, fixed end moment at AB is 0, because that is the hinge part. But BA we have found out minus 3.6, BC minus 3.6. So again CD minus 3.6 and CB minus 3.6. So here initially it is 0 at A, and then it is 3.6. Similarly for D it is 0 and then it is minus 3.6. So minus value of the bending moment is shown outside the frame. So minus value. So here two right angle triangle have formed. Now let us concentrate on the part BC. In the part BC, FEM BC is minus 3.6, FEM CB is minus 3.6. So obviously it will be a rectangle. Correct? Now how we have got this triangle, and we have written over here 8.4. So that part I will explain it to you. If you remember that in step number 2 I have told you that the bending moment at E midpoint is WL by 4. From there we have got the value of 12. Correct? But that was plus 12. So plus 12, and this is minus 3.6. So 12 minus 3.6 gives 8.4. Because here we are drawing, here means in the part BC we are drawing the combined bending moment diagram. Why we have to draw one combined bending moment diagram? Because the part BC is acting at a fixed end beam, and also there is one point load acting. So the combined effect and the combined BMD we have to draw over here. But in case of AB and CD, there is no load acting. So only there is one diagram, that we have got it as a right angle triangle. So the BC part bending moment diagram comes like that way. Now let us just end the problem. What will be the support reaction? Support reaction VA and VD, that will be 6 kilonewton. It is very simple. Why? Because the total load was 12 kilonewton acting at the midpoint. It is a symmetrical loading. So both the support will share the load equally, 6 kilonewton, 6 kilonewton. So that is the first answer. Second answer is how we will find out the horizontal reaction. So horizontal reaction, see BA, we have got it as 3.6. So if we write down the equation, what will be the BA if we take moment at BA? So it will be the horizontal reaction H multiplied by the AB. So AB is 4 meters. So from here we get the horizontal thrust value as 0.9 kilonewton. So this is the final solution, that how to find the support reaction, how to draw the BMD. But remember, this we are solving for a non-sway portal frame. Let us solve another problem. So the question is, analyze this portal frame and draw the BMD and find the support reactions. So as you can see, the first step is the distribution, to find out the distribution factor. If you can remember just the previous problem, the same data I have taken, I mean the values I have taken same, 4 meter, 4 meter, 4 meter, two columns are of 4 meter and the horizontal span is also 4 meter. So the distribution factor first step already we have found out, 3/7 and 4/7, as you can see over here. Now next step, let us start from from the next step. So fixed end moment is what? Fixed end moment, as I have explained you earlier, MAB, MBA, CD, DC, all they are 0 because they are the this point hinge support. So now let us start with the BC part. So FEM at BC, this is a UDL. So if you can remember the step I have told you for the fixed end beam is WL square by 12. So it is minus 20 into 4 square by 12. That gives us to be 26.67 kilonewton meter, and FEM CB will be plus 26.67 kilonewton meter. And also the bending moment at the midpoint of the BC span, that is E, bending moment at E will be WL square by 8. So that is plus 40 kilonewton per meter. I hope you are writing down the problem with me. So while I proceed with the video, it will be easier for you to refer the previous step. Now let us start with the step number 3, MDM moment distribution method. As I have told you, first row will be the joint A, B, C, D. Second row is the member AB, BA, BC, CB, CD, DA. Like that way you write. Third step will be the distribution factor, 3 by 7, 4 by 7, as I have explained you, 4 by 7 and 3 by 7. Next row is the FEM. So the problem starts from here. So you write down the value 0, minus 26.67, plus 26.67, 0, 0. Now as I have explained you in the earlier problem, that first you do the balance carryover. So minus 26.67 you have to balance between BA and BC in what ratio? 3 by 7 and 4 by 7 ratio. So minus 26.67 multiplied by 3 by 7. So it is minus 11.43, but as you are balancing the FEM between the two members, so it has to be positive. So negative FEM has to be balanced by a positive one. Similarly, the positive FEM has to be balanced by the negative one, and with the ratio of their distribution factor. And what is carryover? Carryover is just carrying over the FEM value, moment value, with the half one to the across the member. So like that way, the final moment we are getting at 0, 15.9 over here. So here I want to tell you that if you proceed for one more iteration, so you get this 15.9 as 16. So you can continue for iteration, and then where you find all the values are coming same, you stop over there. Now the last step is the step number 4, that is the BMD and the drawing the BMD and find out the support reactions. So let us have a look over here. As I have told you, A and D are the hinge joint. So what will be the moment? 0, as I have already discussed. Now FEM at BA is 15.9. So here it will form a right angle triangle 0 and 15.9, and minus negative value it is coming. So it is drawn outside the portal frame. So similar is for the column CD, 15.9. Now let us concentrate on the part BC. In the BC part, FEM BC and FEM CB is 15.9. So obviously it will form a rectangle, because here also BC is also 15.9, CB is also 15.9. So a rectangle is formed. Now as it is a UDL, so the nature of the BMD will be a parabolic one. The value we have got it, as you can remember over here, so that we have got WL square by 8 is 40 kilonewton we have got, correct? So 40, but that was positive. So but here in the FEM we are getting it as minus 15.9. So 40 minus 15.9, that is given as 23.1 or 24. So this value we have drawn, the bending moment diagram we have drawn, and what will be the support reaction? Vertical reaction will be the total load. What was the total load? It was UDL. So how it will be shared? WL is the total load. Load intensity multiplied by the span of the BC, that is the total load. That divided by 2 is WL by 2, so that gives us to be 40 kilonewton. Now similarly, like the last problem, if we take moment about the joint B, we get the horizontal thrust as 4 kilonewton. I hope you have understood the video, and if you have any comment or any query, put it in the comment box. You can also mail me at the given email ID, and please keep on watching my other videos on semester 9 and for the other semesters also, semester 3, 5, 7 other semesters also I have uploaded in my website. So please keep on watching and subscribe to get regular updates.